So are you guys listening? Listen up, listen up. So this is when we were graphing transformed linear functions, right? That minus sign in front means I'm doing what? Does anyone remember? Reflecting over the x-axis, okay? Transformations, reflection, translation, right? This number out in front is either a vertical stretch. Remember I had the little squishy thing and I stretched it out? Vertical compression means I'm flattening it down, okay? So if my number in front is more than 1, I'm stretching it up. If it's a fraction, I'm compressing it down. Is this all sounding familiar so far? Yeah. The more you understand about this, the easier today's going to be. We're not going to worry about this little h. Forget the h. But the k, the little plus k on the end, that was a vertical translation. What does a translation look like?
You move it somewhere else.
Yeah, you're just moving it somewhere else, right?
It's like not like a mirror or something. It's just like moving it.
Yeah. If I'm translating something vertically, what are the two directions I can move it?
Up and down.
Up or down. Right? That's this that we're not going to worry about. Horizontal, we're not going to worry about that. Okay, give me a thumbs up if that all sounds familiar to you. Okay. Today, it's going to be exactly the same. But instead of a linear function, we're going to be doing it with an exponential function. Okay? So, this is our equation that we know very well. F of x is equal to a times b to the power of x. Can you do me a favor? Can you guys take out a blue pen and a red pen from your supply box too? If you have your own colored pens, that works even better. I don't care. Okay, are you guys still with me? Okay. So everyone should have 3 colors. At least a red, blue, and a pencil. Does everybody have that?
Yes.
Okay. Or red, blue, and black. If you have a black pen, that's fine. Okay. With our black pen or our pencil, that's going to be our parent function. You guys remember what a parent function is?
Yeah.
It's like a starting point, right?
Oh.
You guys play video games, right?
Yeah.
Most of you do. So when you first open up a video game, right? You have like a base character that you can play as. Sure. I don't know. You guys play like Fortnite and stuff like that, right? I don't know what that is, but as you go through, right, you can get mods and you can get new outfits and new weapons and all that kind of stuff, right? That's what we're going to be doing. We're going to be taking this boring, generic starter character and we're going to be transforming it here, transforming it there, doing a little something here, doing a little something there, okay? It's one way that we can think about it. Let's start out with A, okay? A is our function's y-intercept, like we know. When we compare a transformed function to our parent function, 2 different things can happen with A. A could increase, okay? Or A can decrease. If A increases, we have a vertical stretch. Just like on October 24th, we said if A is greater than 1, that's a vertical stretch. Now, if my A gets bigger, same idea, it's a vertical stretch. And what that does is it moves our function further away from 0, okay? Now, if A decreases, it's going to be a vertical, what do you think? Compression, right? In our parent function, we already have an A. Even if that A value is 1, we have to have some y-intercept that is not 0, right? So if I already have an a there, I'm either going to be increasing my a and stretching it, or decreasing my a and compressing it, or multiplying my a by a number greater than 1 to stretch it, or multiplying it by a fraction to compress it. Is that kind of making sense so far? Well, if it's not, let's see it in action, okay? We got 3 functions here. My parent function, f of x, is equal to 2 to the power of x, okay? Now, what's the invisible number in front of this 2? What's my a value here? 1. Okay, again, we're doing this in black or in pencil. If I were going to evaluate this parent function at 0, what would my output be? It would be 1. If I plug in a 1, I end up with 2. If I plug in a 2, I end up with 4. Ooh. Close. What about if I plug in a negative 1? What do I get? 1/2. I'll call it 0.5. And what about negative 2? 0.25. Okay. Everybody with me on that? Yeah? Let's graph it. Tiny little graph here. In black or in pencil, I'm going to go 0, 1, 1, 2, 2, 4, negative 1, 1/2, negative 2, 1/4. We can see then a nice exponential function through all those points, just like that, and we'll label it off to the left as f of x, again in black or in pencil. I'll move this down so you can see. Boom. While you're graphing that and labeling it, go ahead and grab this real quick. All right, so that's our starting point, right? That's our base character. Haven't done any upgrades yet. Let's see what we can do with g of x, okay? What did we change from f of x to g of x here?
The 1 to a 3.
We turned the 1 to a 3. Okay, do you think that's going to be a stretch or a compression? Stretch, because our a value got bigger, right? 3 times as big, as a matter of fact. So with our blue pens, everybody got a blue pen? Or something not black and not red? A blue pen? We're going to do g of x. Actually, let's do red. My bad. Get the red one. It'll make more sense later. So we're going to do g of x in red. If I plug in a 0, what's now my y-intercept for g of x? Well, what's the number in front? That's my y-intercept, isn't it? 3. If I plug in a 1, 2 to the 1th power is 2. Times 3 gives me 6. What about 2 to the 2nd power? 4 times 3 is 12. Okay, my b value is the same, 2. So I see as I go down, I'm getting twice as big. Twice as big. So what's half of 3? 1.5. Right? And half of that is 0.75. All right, stay with me. So this is g of x in red. Now let's plot those points and see how much different it looks from our f of x. Negative 2, 0.75. Negative 1, 1.5. 0, 3, 1, 6, and 2. How tall is that? 212 is like way up here. Question?
Not real. Maybe just
Okay. So we connect all those red dots together. All the way up there to the top. What does it look like happened to our function now?
It got bigger.
It got bigger, it got taller. We stretched it all the way up. Okay? It's like we took this black line, right? We held it by the arrow, and we physically pulled it and stretched it. You guys okay over there? It's like we took this arrow in our parent function and we pulled it up, 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 and stretched it all the way up. You guys can kind of visualize that, right? Okay. So g of x is a vertical what? Stretch. What's my scale factor that I'm stretching by? 3. Thank you, Colby. 3. Because my original a value was 1, now it's 3. Essentially what the scale factor is asking is, well, what did I multiply my parent function's a by to give me my new a? Well, we multiplied it by a scale factor of 3. Now with our blue pen, we're going to do h of x. We're going to see what happens when we compress this, when we squish it down. What is my y-intercept for h of x? 0.5. If I plug in a 1, I get 0.5 times 2, which is 1. If I plug in a 2, I get 0.5 times 4, which is 2. What do I get when I plug in negative 1? 0.25. And if I plug in negative 2, I get 0.125. Very close. 0.125. Everyone good on how we got those? Yeah? Well, now let's plot these points. 0, 0.5 in blue. 1, 1. 2, 2. Negative 1 and a quarter. Negative 2 and almost 0. What happened to my blue line now if we look at it? It's a vertical compression. We squished it down, right? It'd be like if I took this black line and I just pushed down on it and squished it. That's what we end up with, that blue line. This is a vertical compression. What's my scale factor this time? 0.5. Or 1/2. Either one is fine. Right? At least for me personally, I find graphing decimals a lot easier because I can approximate where it is, right? But if you feel more comfortable graphing fractions, that's up to you. That's your thing. Quick show of thumbs. How we feeling about that? Thumbs up, that makes a lot of sense. Thumbs down, that doesn't make any sense. Thumbs sideways, you just woke up. Okay. Most of us, some sideways. It's okay. Here comes the second piece. Glue this in while people are finishing up so we can get going. There you go. Anybody still gluing in? All right, let's keep going. So, just like on, again, October 24th, that fateful day, if there's a negative sign in front of my a, what happens to my function? It reflects across the x-axis. So here, when we're comparing to a parent function, if my a is negative, it's reflected across, what do you guys think? What are we reflecting it across? That's right. Same as before. If my a value turns negative, I'm now reflecting it across the x-axis. We treat this negative sign as a completely different transformation because it is, right? If I have a parent function where it's like 3, wait, no. If I have a parent function that's like 2 times 2 to the x, right? And then it turns into negative 3 times 2 to the x, right? The negative tells me I reflected over the x. Would this be a stretch or a compression? It'd be a compression because it's negative, right? That's exactly what you would think. That's why we keep them separate. The absolute value of my a is kind of what we really should be talking about. This is going to be a vertical stretch that also happens to be reflected over the x-axis, right? So the negative sign is its own thing. When I'm comparing my a's in front, you ask, did it increase or did it decrease? That tells you whether it's a stretch or a compression. Ignoring the negative sign completely. Give me a thumbs up if you understand what I say or what I mean when I say all that. Okay, well, half of us is 50%, either way. So, if you take a look, my parent function, we're using the same one as before. So I already know what my values are going to be, right? This is going to be 0.25, right? We're going to do this in black. 0.25, 0.5, 1, 2, 4. So if I plot those points, -2 up to 1/4, -1 up to 1/2, 0 to 1, 1 to 2, 2 to 4. Bless you. Now g of x we're going to do in red, just like before. And again, we talked about this the other day. My negative sign is not in the parentheses. So whatever I plug in for my exponent, I'm taking the power of 2, and then I'm multiplying it by that negative, right? Excuse me. So if I plug in 0, what's my output going to be? -1. Thank you, Abigail. -1. If I plug in 1, right? 2 to the first power is 2, times -1 gives me what? -2. What about if I plug in -1? 2 to the -1 is just 1/2, times -1 is what? -0.5. What's happening to my outputs?
It's getting all turning negative.
They're all turning negative, right? Because we just took the parent function that we had and then multiplied it by -1. So this is going to give me -0.25 and -4. Well, let's plot those points and see what that looks like. There's my y-intercept, -1, -1/2, -2 1/4, 1 -2, 2 -4. You guys see the nice symmetrical image we just made? Yeah, what's my line of reflection for this image? The x-axis. Right, if this x-axis is my mirror, the image on the top is going to flip over, make that image on the bottom. Again, this is called my line of reflection. So again, this is completely separate from the stretching and compressing. I could definitely stretch something and reflect it. I can compress something and reflect it. Just depends on what your parent function is and what your new function g of x turns into. That one's pretty straightforward. What questions can I answer about the reflections? The homework is super easy, so don't worry. I know we're going long, but it's very simple. Anyone still writing all that? Cool. Last but not least, this little k here on the end. This little k right here. Okay? Okay? So the k value is added to the end of our parent function, and what that tells me is that I'm translating up if I'm adding and down if I'm subtracting. I'll flip back, don't worry. If I go to, what was the day? October 24th. That's right. This plus k on the end is a vertical translation. Okay? If I'm going up or down, that's a vertical move. One or the other. So, go ahead and graph f of x is equal to 2 to the power of x. We've done it twice already. You guys can do that. Right? My parent function in black. G of x we're going to do in red. H of x we're going to do in blue. So just use these points directly above it. We have the 5 points already. All right, everyone good on f of x? Yeah? I'm going to assume that means yes. So for g of x, I'm going to go one by one, plug these in, and then I'm going to add 2. Okay? If I plug in 0, 2 to the 0th power is 1. 1 plus 2 gives me what? 3. If I plug in 1, 2 to the first is 2. 2 plus 2 is? 2 plus 2 is? Okay, good. If I plug in 2, 2 squared is 4. 4 plus 2 is 6. If I plug in negative 1, what's 1/2 plus 2?
2.
2.5.
What? Yeah, it's 2.5.
If I plug in negative 1 here, 2 to the negative 1 is 1 over 2, which is 0.5. 0.5 plus 2 is 2.5. And if I plug in negative 2, I get 0.25 plus 2 is 2.25. So take a look. I took all these outputs here and I added what to them? 2. We just increased them all by 2. Go ahead and plot those points. See what it looks like. 0, 3, 1, 4, 2, 6, negative 1, 2.5, negative 2, 2.25. So my parent function, what was my asymptote, if we remember what we talked about? What's my asymptote for the parent function in black? What line is it never going to cross? The x-axis, right? At 0. At y equals 0. What line is g of x never going to cross? 2. Right? Y equals 2 is my line, my horizontal line right here. Well, why can't y equal 2? Tyler?
Because if you look at f of x, it can never reach 0. And if you just add 2, it's just adding 2 to y. So
Yeah.
it would never be able to reach 2.
Exactly. If I look at f of x, right? If I take out f of x and replace it with 0, what can I plug in for x that's going to give me 0? 2 to the power of what equals 0? Nothing. This is undefined. 2 to the power of 1, as we know, is 1. 2 to the power of 0 is 1. I'm never going to get 0. But if I go over here to g of x, if I plug in 2, 2 equals 2 to the power of x plus 2. Just like Tyler said, and I subtract 2 from both sides, well, now I'm left with the same thing. This is also undefined. So when I translate my exponential function up or down, the asymptote is coming with it. Does that kind of make sense? If it doesn't, that's not the biggest deal. Let's do h of x. Now I'm subtracting 2. What do you think is going to happen to my parent function here?
It's going to be translated to units down.
We're not going to compress. Compressing is changing the number in front. But if I have this number in back and I'm subtracting, I have a negative number, what direction do you think I'm going to go?
Down.
I'm going to go down.
2 units down.
This one I went up. This one I'm going to go down. Let's plug them in. 2 to the power of 0 is 1, minus 2 is negative 1. 2 to the power of 1 is 2, minus 2 is 0. 4 minus 2 is 2. 1/2 minus 2 is negative 1.5. 1/4.
Negative 1.75.
Yeah, negative 1.75. And again, we just took our black outputs from the previous section and subtracted 2 from them. 0, negative 1. 1, 0. 2, 2. Negative 1, negative 1.5. Negative 2, negative 1.75. And again, my asymptote also dropped to negative 2. 2 spaces down. You don't really need to label them if we use the colors correctly, right? But I wanted to. Now, if we really want to get crazy, we could talk about end behavior, right? For g of x, as x approaches infinity, f of x goes to positive infinity. But as x approaches negative infinity, what is y approaching? 2. Exactly. For h of x, as x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, what is my y getting closer and closer to? Negative 2. Good. That means you understand end behavior, which is great. What questions can I answer?